All right, welcome back, everybody. At long last, we have finally come to the definition of chaos. In the past few videos, we've been looking at all the different kinds of behaviors that we can expect out of deterministic systems. And we see asymptotic behavior, we see cycling behavior, we even see quasi-periodic behavior, but none of them constitutes what we would like to call chaos. And in this video, we are finally going to define it. So, chaotic dynamics are extreme in some sense, but they are actually extraordinarily subtle and really difficult to pinpoint a precise definition in a completely different sense. So, with this in mind, we would like our definition to reflect that subtlety and that extreme in that sense of extreme and subtlety. So we're going to define chaos based on how Robert Devaney defines it. And Robert Devaney, you should definitely be listening to what this guy says. He is he's one of the founding, not really the founding fathers, but definitely one of the leading experts and pioneered a lot of the modern smooth dynamical systems theory. And he's got textbooks. I mean, you really should be listening to what he says. Him, Hirsch, Smale, all of them just powerhouses. Arnold, another one, Kolmogorov. But I digress. Oh, Moser would be another one then. But Bob Devaney defines chaos in the following way. He says that a deterministic dynamical system is said to be chaotic if it has dense periodic orbits, if it is topologically transitive, and if it exhibits sensitive dependence on initial conditions. Right, so the first thing to note here, we are talking about deterministic systems, and what that means is that nothing about chaos is random. As much as we would like to say the behavior is so erratic that it looks random, chaos is deterministic, right? If we had the position and momentum of every object in the universe, we would be able to predict exactly where it is based on Newtonian mechanics. And that's correct, right? I mean, we have a mathematical theory to back that up and say, yes, definitely, we know exactly what's going to happen. But actually figuring out what it looks like in practice is what makes this so difficult. And chaos is behind that mechanism, or the mechanism behind that impracticality. So apart from being deterministic, so non-random, the first item in that definition is going to deal with the ubiquity, right, or just they're everywhere, the ubiquity of periodic solutions in these systems, and they are going to be unstable, right? So we want to make sure we're going away from periodic behavior. A lot of the time, some definitions will actually go out of their way to say that our system exhibits aperiodic behavior, right? And it's in that same sense as quasi-periodicity, right? We're not quite periodic, or just in general, there is no repeating of behaviors. So even though many solutions are aperiodic, first item shows that we can approximate these guys, right? Any of the solutions in our phase space can be approximated arbitrarily closely by periodic orbits. We can get very close using a solution that is periodic. And that's what the density term is going to mean, or what density means in this case. So, for example, we saw an example of dense periodic orbits in the previous section. So, for any point on the torus, there is a sequence of points lying on a sequence of periodic orbits with slope qi over pi, say, such that those points are going to tend to x, or there is that sequence, xn, that tends to x. So in other words, each point on the torus is approached arbitrarily closely by points that lie on periodic orbits, right? Again, subtlety here. So it might be a little easier to see what we mean by dense periodic orbits in the following sense. So we can actually see it in the logistic map very, very clearly. So we are going to look at a map, and so it's a nice discrete system instead of a continuous system. And we're going to use r equals 4 on the logistic map, right? That multiplier we saw earlier in the semester is very much within what we would like to call a chaotic regime. So we can start computing some periodic orbits here. In this one, it's going to be a whole bunch of numerical root finds to figure out what these points are. But you can go ahead and figure out that there is a periodic orbit of period 2. There's one of period 3, of period 4, 5, 6, 7, 8, and we stop at 8. So sorry, we don't go and compute all of them. But what I'd like for you to pay attention to here is not the numbers involved necessarily, not what makes up the cycles, but I'd like to show you that we can get arbitrarily close to, where am I going? I can choose a point, say 1/10, so 0.1, right? And that's exactly what I have down here, is that there is a sequence of points that belong to orbits of different periods, but that those points approach 0.1. Now, I think you can go ahead and show that 0.1 either has an arbitrarily long period that's really hard for us to compute numerically, or just flat out does not have, is an aperiodic initial condition, or an initial condition that's associated with an aperiodic orbit. So the point is that I can go ahead and start jumping here. I can start at x0, or I can say what x0 is. Then I can jump down to x1, and that's closer to 0.1. And then I go over here to x2, and that's even closer. x3, oh, we're getting really close, 0.117, okay, x3. 0.4, we jump to the other side. That's actually about the same distance away from 0.1. So technically I could skip over 3 or 7, or I omit them from my sequence. So there's x4. I go to x5, 0.11. Okay, we're getting good. We're going really good here. And then I have 0.6. I think I should actually reorder. Yeah, I should probably reorder x5 and x6 here, because this guy is a little bit too far. Yeah. There's x5, and then x6. Oh, shoot. And there we go. Here's x6. But the point is that these points, I can find some sequence that converges on 0.1, all of whose members belong to different periodic orbits. And that's what we mean by density in this case, that we can approach any point we want with an arbitrary degree of accuracy or precision, with an arbitrary degree of accuracy by following periodic orbits. So in this sense, the periodic orbits fill the phase space, right? If I close that, right? If I take the limit, right? If I fill in my periodic orbits, or I use my periodic orbits and then I attach to them all of their limit points, the limit points that they could create, so make the metric closure for this system or for this phase space, I would find the entire phase space. Okay, so now we go back to item 2 here. Topologically transitive. So transitivity, you may or may not see that in equivalence relations when you talk about proof, mathematical proof. But in this case, it means something a little bit different. Kind of similar, but it's more specific. And in particular, topological transitivity is just a way for us to make sure that our system looks like it's wandering, that our solutions want to wander around and visit everywhere with a certain kind of equality, a certain distribution of solutions trying to travel throughout the phase space. So we say that a system is topologically transitive if for any open sets A and B sitting in the phase space omega, there is a solution that begins in A and eventually passes through B. Okay, so that's exactly what we would like here. We'd like to say that no matter where we are in the system, there is some solution that starts there, and if we have a particular target in mind, we'll forget that original solution. So say we have this target set A that we're trying to start in, or we have a starting set A and then a target set B that we'd like to get to. We're saying that there is some solution that starts in A and then eventually hits in the target, or it goes through B somewhere, right? So this is just a way for us to say that there is kind of an equal distribution of solutions that will visit everywhere in the phase space. And this is essentially a mixing condition. So this captures the wandering characteristic that we would like in chaos. And we saw this before in the dense orbits on the system, on the coupled oscillator system. And we put the phase space on the torus. And the maps theta 2 equals omega times theta 1. So if I put an irrational slope on this solution curve, then I do get a transitive orbit, right? So I can visit whichever location. We proved that effectively with the Poincaré map, right? We showed that the Poincaré map had a dense orbit for any initial condition if we were using an irrational slope. And this is a really great jumping off point if students want to go ahead and take a look at ergodic theory. And this is essentially the math of mixing things, the math of making sure things are distributed or how things distribute. It's very much a branch of measure theory and probability theory. So, and it's actually definitely worth your time. It's quite technical in places, so it might be a little tricky to get a handle on without some from graduate analysis. Specifically in measure theory. But for now, we need to really get a handle on not conditions 1 and 2, but condition 3 here. This is one that we've kind of dabbled with, and we've been kind of batting around for a little while, saying, we're going to kick this, or we're going to punt on this guy a little bit until we get to this point, right? So we see systems that look like they are sensitively dependent on the initial condition, and this would look something like, or we would assume that this would be the case for the irrational slope solutions for the coupled oscillator. But we showed at the end of the last video that these solutions on the coupled oscillator were actually parallel. If we just choose a different initial condition, we would get parallel solutions. So these solutions don't deviate even if you're a little bit off in your initial condition, your approximation of an initial condition, which is the case when you put anything into a computer. There is always going to be some amount of error in your computation. Now, this sensitive dependence on initial conditions deals with the long-term unpredictability of our system. So, and I say unpredictability, this really should be practical unpredictability. Right. So again, if we were the the wise, all-knowing being who could take whatever initial conditions of the universe you want and say, okay, yes, this is exactly what your system looks like. Life is boring after this point because I know exactly what's going to happen. This is what makes life interesting. Right. Sensitive dependence on initial conditions are actually seen very easily in the logistic map that we have been using from upstairs. So what I'd like to show you is what this means, like specifically what this means. So I have plotted in MATLAB a pair of solutions here, both corresponding to the R equals 4 logistic map. And the blue curve is going to be this nice 0.2 initial condition, and the red curve is going to be 0.200001. So 2 plus 10 to the minus 6, or 0.2 plus 10 to the minus 6, excuse me. And this is approximately the same as the blue solution, at least at first. So we can see that these two solutions do look very similar to one another initially, but that very, very quickly they start to kind of deviate from one another. And then they express completely different dynamics thereafter. So even though these two solutions are deterministic, or the system is deterministic, and I'm using two initial conditions that are basically the same as far as my human eye can tell, the computer is going to suss out the error and magnify it at an exponential rate. And this is exactly what we try to set out to measure. So maybe we think, okay, so maybe Doc Sheep is terrible at approximating solutions, and he just didn't get the solution close enough. He started with 2 plus 10 to the minus 6. Now, he really should have started with something like 0.2 plus 10 to the minus 10 on the red orbit. So sure, that does buy you a little extra time, but not much. Notice that these guys start to deviate once more. Right, we can start to see that they look different after about 27 iterations, and then they exhibit completely different dynamics. Right, you can see it especially the case between these two differences here. And we would like there to be some way for us to quantify how that happens or what that deviation looks like. And it turns out we're smart. We can do this. We actually can figure this out. So is there an objective way to measure how long we can expect nearby solutions to stay close together before they deviate? And yes, actually we can. And to answer this, let's see what the error looks like. So specifically, we're going to do this on the, which system are we going to do this in? It would appear to me that we're doing this in the 10 to the minus 10 deviation, right? So in that system, we're going to go ahead and plot the error there between the red orbit and the blue orbit. So I'm using superscripts, not as powers of x, but as indices, so be careful. I'll try to mark everything in red for the first curve and blue for the second curve. And notice that this looks like a gigantic mess. The error that I plot is just going to be the absolute value between these, between the difference here, or of the difference between these two guys. Sure, that's how you measure absolute error. But notice what happens initially. We are capturing the fact that these guys stay close together for a certain amount of time, but then let's zoom in a little bit. Let's zoom in a tiny, tiny bit. Don't know about you, but this portion of the curve, which is what's graphed down here, that looks roughly exponential to me. So one might think, okay, so if solutions are going to deviate, at least initially, they're going to deviate in some sort of exponential fashion. And that is the case. We can actually measure that. So let's use the model that the error is approximately some exponential function with magnification factor lambda, or rate factor lambda. And we can go ahead and construct a regression curve, an exponential regression, to this guy, to say that, oh shoot, I'm still on the eraser, to show that the error is actually an exponential function of n. And this is actually a fairly decent approximation, strangely enough. So how did I do this? Well, this is plain and simple. I got this through a log linear plot regression. And I did this with polyfit. And there's something here, and then I did a linear regression on the log linear plot. So yes, you can do this in MATLAB, and I recommend you give this a shot. If you would like to try it out, be my guest. But we're already running the video a little bit long, so I'm going to keep going. And you can see that this is a relatively good approximation to the error term. Right, that little blue curve is actually following red pretty faithfully, strangely enough. So what we would like to say is that if the error has a positive rate constant, that positive lambda, then these solutions are going to exponentially deviate from one another. But if that exponent is negative, then these guys are actually going to approach each other, and we have a nice stable, robust algorithm, or a non-chaotic system even, because these initial conditions are not going to try to push nearby solutions away from each other. So this lambda, we're going to go ahead and call this the Lyapunov exponent. And this is what is known as in the literature. And it's telling us when the system wants to push initial conditions away from each other, or how strongly it wants to do that. So when this Lyapunov exponent is positive, like we have up here, about 0.7019, right? That's a positive number, so that means that the error is going to grow exponentially, at least initially, and hence indicates that we have a sensitive dependence on initial conditions. So in the more general setting, consider an arbitrary map, xn plus 1 is f of xn. Our scenario then is the red curve here, right? We're going to have a red curve and a blue curve, where the blue curve initially deviates from the red curve on the initial condition by some small delta 0 or delta naught. So if we are going to go ahead and define how far these solutions like to deviate from one another, then we're going to go ahead and define the error to be effectively this guy. But this is a little bit different than E sub n. This is not the absolute value. It's just the straight up difference between these guys. However, I immediately go ahead and hit this with an absolute value, so it is effectively the same computation. But in general, look what happens. If delta 0 is sufficiently close to 0, right, if we have a very small difference between the initial condition on the red curve and the blue curve, then assuming the model that this guy is exponential, notice what happens. The ratio of delta n to delta 0 is exactly what it means for us, or it's going to be an exponential change, right? This is exactly what we expect to see upstairs. But notice that this guy is very, very close to our definition of the derivative, the limit definition of the derivative of fn computed at delta, or at x0. And this is exactly what the approximation is saying here, is that I can jump from this line to the next by making delta 0 very small, so that approximately the derivative of the nth iteration of f of x0 is approximately exponential. So if I hit both sides with a log and divide by n, then sure, I get the following expression for what lambda should be, at least approximately. And this is what we can throw into the computer. We can actually go ahead and go a little bit further. We did work on this, this derivative term way back when we talked about stability of periodic orbits for one-dimensional maps. And this derivative simplifies to the product of the first derivative of f on each one of the members of this orbit. So it's the derivative at x0 times the derivative of f at x1, f prime times f prime of x2 times f prime of x3, and so on until I hit however long the orbit approximation is. Which means that if I'm hitting this with a log, the log of a product becomes the sum of logs, and we now have the definition of the Lyapunov exponent. Like the formal definition of the Lyapunov exponent is this limit as the length of the orbit goes off to infinity. Now, Steve Strogatz explains an algorithm in his textbook about how we can approximate this guy. There is a quick algebra or a quick algorithm that will allow us to compute this exponent. And it turns out that if we do a little bit of experimenting, that exponent turns out to be independent of the choice of our initial conditions, surprisingly enough. Right? Seeing how our definition depends on where we start, right? It depends on the specific orbit of our initial condition x0. That should be very surprising. So, it'd be interesting to figure out why that's the case. But then we'd have to talk about transient chaos, which we may or may not get to. We'll see. But Strogatz does give an algorithm for how you can compute this guy, at least approximately. So, but what I have on the plot here is something I picked up in MATLAB, where I went ahead and used our bifurcation or orbit diagram program that we had from earlier in the semester to create the bifurcation diagram or the orbit diagram for the logistic function on a range of r values. Right, so down here, I really should label that. Here's r. So the horizontal axis is r going from 3 to 4. And notice what happens here. This blue curve, or the blue mist here, the blue dust, is the bifurcation diagram, but the red curve here is actually the numerical approximation of the Lyapunov exponent for each value of r. And notice what happens. This guy is negative up until about here. And notice what happens at that point. We go from nice period doubling to what appears to be a fractal pattern in the bifurcation diagram. And if we go all the way over here, you can kind of see it. I'll blow it up a little bit. You can kind of see the red curve sitting underneath the blue dust. Notice that that occurs at approximately, based on the program I ran, that occurs at about, or the Lyapunov exponent there is about 0.6931, and you can check, that's roughly natural log of 2. And that is remarkably close to our estimate that we had upstairs in the regression plot. That is not too shabby, folks. Not too shabby at all. So the point to take away from this is that sensitive dependence on initial conditions appears to be exponential, but only initially, right? There's an entire, there's an entire discussion to be had about transients and about when we can actually believe this when we can believe this to be an exponent. Oh geez, I did it again. Believe this to be an exponential deviation from the of the two solutions from one another. But bottom line here, and I'll actually go to the bottom line, is that lambda being positive seems to be a good indicator of sensitive dependence on initial conditions, and for this case is a strong indicator of chaotic dynamics. And a lot of the time, that's exactly what the Lyapunov exponent is used for in practice, is to establish that sensitive dependence on initial conditions and to at least indicate or suggest that the system incurs chaotic dynamics for some parameter regime. So what we would like to do now is see how we can find chaos, or how we can prove chaos exists within certain systems. So next video, we're going to go ahead and start talking about the world famous, most infamous of chaotic systems. We're going to talk about the Lorenz system. And I'll go ahead and see you in that next video.